Hello, and welcome to Western Civ, episode 263, Facts and Experiments. In our last three episodes, we took a look at the beginning of the scientific revolution by examining first the nature of discovery, then how Europeans changed their views of our planet, and finally how math, for really the first time in history, started to become an essential and independent branch of science. From perspective painting to ballistics, no one doubted in 1600 how important mathematics had become to humans' existence. But if the revolution begun by the mathematicians was to be successful, it needed to identify other ways of establishing and communicating universal truths. And that is what we will be covering today. One day early in 1610, Johannes Kepler was walking across a bridge in Prague when a few snowflakes settled upon his coat. Watching them, Kepler evidently grasped two things more or less simultaneously. Each snowflake was unique, but they were all alike in that they were all six-cornered. This got Kepler thinking about two-dimensional six-cornered shapes and how they form a lattice, the cells of a honeycomb or seeds of a pomegranate, and about how the only shapes that one can use to tile a floor, if all the tiles are the same, are triangles, squares, and hexagons, and about the patterns you can make if you pile cannonballs on top of one another. Kepler thought he could work out the most space-saving way of piling spheres. His claim would later become known as the Kepler conjecture, and was finally proven true for any regular lattice in 1831 and for any possible arrangement of spheres in 1998. For Kepler, this was applied mathematics. Like Galileo, Kepler believed that nature was based in geometry. If God was a mathematician, and who could doubt that, then one would expect to find math everywhere, from the organization of our solar system to the smallest snowflake. Math, in this case geometry, has to be there. We're going to go more in detail into Galileo a little bit later on, but to get to the idea of experimentation and fact, here's a quick overview. The story of Galileo's discoveries is straightforward. In 1608, the telescope was invented in the Netherlands as sort of a chance discovery. Galileo's first telescope had a usable magnification of 8 times by the beginning of 610. And eventually, he managed to produce one that had a magnification of 30 times, with which he could begin to explore the heavens. There's a standard phrase used over and over again in literature, quote, "Galileo turned his telescope to the heavens," end quote. Of course he did. Same thing was going on in England, where another astronomer named Harriot did the same thing 4 months before Galileo, and his first telescope had a magnification of 6 times. The puzzle lies in the enormous effort that Galileo put into improving his telescope, grinding on his own equipment 200 lenses in order to end up with 10 telescopes with a magnification of 20 times or better. For what is strange about these 10 telescopes is that they're too good for their obvious military use. Their field of view was tiny. Galileo could only see a small part of the moon at one time. Held with 2 hands, they shook and wobbled, so that anything you looked at kept slipping out of the field of view. He realized some sort of tripod or mount was essential. It is important here for a moment to distinguish between the impact of the telescope and the microscope. The two are basically the same thing. So as soon as Galileo had a telescope, he could use it to study flies, for example. He later devised a better tabletop instrument and studied how flies could climb up glass. But the first publication to represent what could be seen through a microscope, a single broadsheet which was entitled the Aparium, about bees in honor of Pope Urban VIII, didn't appear until 1625. And the first major publication was called Micrographia, and that wasn't published until 1665. It's interesting because the telescope, on the other hand, transformed astronomy almost overnight, while the microscope was slow to be adopted, and actually, toward the end of the century, quick to be abandoned. The reason for this, I think, is simple. There was an established body of astronomical theory, and what was seen with the telescope was at odds with it. Astronomers could scarcely dispute the relevancy of the telescope to their studies. But the microscope brought into view a world that was previously unknown. It was hard to establish how the new information it produced related to established knowledge. The telescope addressed directly issues that were already under discussion. The microscope, on the other hand, opened up new lines of inquiry whose relevancy to current concerns wasn't as obvious. A microscope simply isn't as helpful when you're trying to sight your cannonballs. That the telescope flourished and the microscope languished is one of the signs the scientific revolution can be properly understood as a revolution, a revolt against the previous order. I think that's something that I've come back to every episode in this, whether we're talking about math or the planet Earth. The reality is the scientific revolution is a revolution because it's a rejection of what were thousands upon thousands of years of assumed knowledge. Both the telescope and the microscope produced new knowledge, but in the 17th century, only the telescope directly endangered the existing order. When Galileo pointed his improved telescope at the moon in 1609, he spotted something much more striking than he had seen before. Where there should have been light on the surface of the moon, there was darkness, and vice versa. What Galileo realized immediately was that the moon wasn't flat, not flat at all, which had previously been taken for granted. There were mountains and craters. The moon, in other words, was much more like our planet Earth than we had previously thought. And it just so happened that in England, the astronomer Harriot had seen exactly what Galileo had seen. We have a sketch that he drew on the 26th of July, 1609. Looking at it, it's perfectly clear that the terminator, that is the part where you can see light, is not regular. It's irregular. This is confirmed in another sketch by the same man dated the 17th of July, 1610. The difference is, by the time of the second sketch, Harriot had read Galileo's Starry Messenger, which had been published in the spring. Now, looking at it from Galileo's perspective, he saw exactly what Galileo had seen. It seems clear that what he was doing was comparing Galileo's illustration with what he could see through his telescope. For both Galileo's illustration and Harriot's illustration feature a large circular shape. In fact, there's no such prominent object on the moon, and scholars have suggested that Galileo deliberately enlarged a crater to enable the viewer to, as it were, zoom in. Harriot, looking at the moon, saw the same: the highlights and shadows, the mountain ranges, the valleys that Galileo described. And he also convinced himself that he had seen Galileo's imaginary crater. Once Galileo had described what he had seen, once he had trained viewers on how to look, it was almost impossible to dispute that the moon had mountains and valleys, even one that didn't really exist. Of course, all this paled in comparison to the revelations that lie ahead. In October 1611, Galileo came to the conclusion that one could predict the location and movement of the heavens, and one could do it with much greater accuracy than had been hitherto thought. By this point, Galileo realized Venus had phases, and that these phases were totally incompatible with Ptolemaic astronomy, which assumed Venus had to orbit around the Earth. Looking at these phases, Galileo realized Venus absolutely had to orbit around the Sun. Early the following year, when Galileo told a prominent group of Jesuit astronomers about this discovery, and they confirmed it, they threw him a party. Not everyone, as we will see, even within the church, was hostile to new ideas about the universe. Just some people. But make no mistake, after 1611-1612, the Ptolemaic conception of the universe had been fatally wounded. Interestingly enough, Galileo's discovery also marked the first time in the history of the world, in 1628, Francis Godwin published the first ever work of science fiction, titled The Man in the Moon. Later on, these mathematical innovations would lead to the creation of the metric system in the early 18th century, so that scientists could consistently measure and explain their new discoveries. Previously, historians thought that Copernicus was responsible for the destruction of the correspondence between the microcosm and the macrocosm. This is a mistake. There was only one small major shift in Copernicus's universe. The stars were required to be at a vast distance from the solar system. Given that there was no measurable change in their relationship to each other in the sky, while the Earth orbited the Sun in the course of a year, and consequently, they must be very big if they're not invisible. But the Sun and the planets remained the same size, and Copernicus still continued, it seems, to believe that the universe consisted of nested spheres, which was Ptolemaic 100%. Copernicus's universe was no longer Earth-centered, but it was Earth-friendly, and there was no reason to think that it was not the product of benevolent design. There was nothing in his argument that might imply that Earth was just another planet, or that the universe had not been created for the benefit of human beings. The universe had a center, and the Sun and the Earth were still unique objects. The key change occurred in 1608 with the invention of the telescope and the microscope. Before 1608, the standard scientific instruments, crosstabs, astrolabes, and so forth, were all designed to make naked eye measurements of degrees of a circle. Even the vast sextants and quadrants built by Tycho Brahe were simply enlarged sighting devices. These instruments were really no different in principle than those used by Ptolemy. And although, by making parallax investigations of the comet and stars, they could be used to undermine traditional belief in translucent spheres that supported all the planets, as was still accepted by Copernicus, they reinforced the assumption that human beings were the perfect observers of the cosmos, and the cosmos itself was designed to support human life. But after 1608, a new range of instruments made the invisible visible. The thermometer, 1611, and barometer, 1643, made it possible to see temperature and air pressure for the first time. All of these intellectual changes have consequences. The discovery of America killed off the two-sphere theory of the Earth. Copernicanism led to the belief that the planets shine by reflecting light, which was confirmed by the discovery of the phases of Venus, and this would kill off the Ptolemaic system. But the phases of Venus, which is what really kills off the Ptolemaic system, was only made possible because of the telescope. Innovation and invention changed the conception of the universe. The reality is, Ptolemaic astronomy was unaffected by Copernicus. Certainly it went into crisis when the new star was discovered in 1572, but by the end of the 16th century, it had fully recovered. The telescope, on the other hand, brought about its immediate and irreversible collapse. And this is another fascinating point about the scientific revolution. Once mankind figured out that it could look to the heavens, what it decided to do was find new, innovative, and better ways of doing so. And that brings about a further shift in consciousness, which brings about more investigation. In other words, For the first time, as we're going to see, humankind is starting to experiment with science. And that experimentation is going to blow the lid off everything medieval Europe believed. We take facts for granted nowadays. There have been few attempts to write the history of facts, and all of them are frankly terrible. Yet our culture is as dependent on facts as it is on crude oil. It's almost impossible to imagine doing without facts. And yet, there was a time when facts didn't exist. What did the map of knowledge look like before the invention of the fact? On the one hand, there was truth. On the other, opinion. On the other hand, there was knowledge. On the other, there was experience. On the one hand, there was proof. On the other, there was persuasion. Opinion, experience, persuasion, all of these were necessarily unreliable and unsatisfactory. Knowledge had to be built on firmer foundations. The story of the fact is a story in which the lowest and most unreliable form of knowledge was magically transformed into the highest and most reliable. What we're concerned with here is what the Oxford English Dictionary lists as fact. Quote, a thing that has really occurred or is actually the case, end quote. Although dictionaries don't distinguish clearly enough between an agency of a fact, something that has occurred because someone has done it, and an impersonal idea of fact, something that has occurred in the course of nature. How did you refer to this something before facts were invented? In Greek, there was the phenomenon, but phenomenon were malleable. They could be saved or solved, while facts are stubborn. In Latin, there is the thing, res. The Romans said res ipsa loquitur, which means the facts speak for themselves. Of course, when they wrote this, there was no such word as fact. In English, before the fact, there were particulars. Phenomena are too subjective. They are appearances, not realities. Things in particulars are too much in the real world. None of them corresponds to that peculiar blend of reality and thought, which is the fact. This peculiar blend is what some have referred to when describing facts as linguistic, but claiming to be copies of the real. In a society becoming increasingly interested in experience, it should come as no surprise that the term fact was taking on a new significance. Facts identify a type of knowledge which is grounded in experience. Whereas before, Europeans might have obsessed about relations of ideas, now they wanted matters of fact. In fact, pun intended, Hume indicated the distinction between relationships and ideas and matters of fact was fundamentally the intellectual conflict that gives rise to the scientific revolution. Amazingly to us today, before the scientific revolution, facts were few and far between. They had to be handmade. For example, they were hard to distribute and they were unreliable. A good instance of this is just simply the fact that prior to 1801, it's impossible for us to say from a historical perspective, even though we have a lot of facts about the industrialized West, before 1801, we cannot definitively say what the population of Great Britain was. Crucially, facts are not only established, they can be disestablished. A fact can be confirmed by experience, and then it can be refuted by experience. When and where was the language of the fact invented? Only quite recently, historians thought there was a straightforward answer to this question. Francis Bacon invented the fact. From Bacon, the fact entered the English language and was adopted by the Royal Society. So historians started to write about, seriously, quote, Baconian facts, end quote. English philosophy has always been thought to be almost peculiarly empiricist, and therefore it made sense that on this count, England would have created and invented the culture of the fact. Unfortunately, this story, as with most straightforward answers, is just way too simplistic to be accurate. The fact doesn't belong to the English language. Galileo and his correspondents happily discussed facts, but there are Italian usages from much earlier, from the 1570s. According to established scholarship, the French discovered the New World only in the 1660s, but Montague used the word fact, F-A-I-C-T, to mean fact no less than 5 times, one of which actually dates from as early as 1580, well before the 1660s. When it comes to linguistics, you really have to get the initial usage, which it turns out is a lot earlier than what we thought. In fact, the word fact itself doesn't come from Bacon. He never uses the word in its modern meaning in English. He uses factum 3 or 4 times in print. The man with the stronger claim to the word fact is Thomas Hobbes. He uses the word in Elements of Law, Natural and Politic, written in 1640, but not published until 1650. Of course, there were facts, as I mentioned, in Italian, French, and Latin long before there were facts in English. The word fact only becomes more respectable in English after 1661. And again, here the printing press is extremely important. The printing press made facts, according to one historian, harder. Before printing, facts were too soft. They were too malleable. What made the scientific revolution, this historian argues, is not the experimental method or commercial society. Both of those have been around for centuries. But again, the printing press, which turned private information into public knowledge, private experience into communal experience. For my case, I don't think that this takes the argument far enough. The printing press didn't necessarily make facts stronger. It made them, outside of very few specialized fields, possible. Without the printing press, I'm not sure the modern conception of fact ever comes into being, because you just can't disseminate enough knowledge along enough of the population. It just isn't going to work, not without the way to mass produce facts. And the printing press allowed for the mass production of facts in the way that the factory system is going to allow for the mass production of Model T cars later on. Gutenberg's Bible was completed in 1454 or 1455. That was, of course, a watershed moment. But consider this. When a major comet passed by Earth in 1577, thanks to the printing press, which had now been in operation for at least 22 years, more than 180 publications debated the meaning of its existence. Thus, the printing press took astronomers and astrologers, scientists from 2 different fields, and put them together to exchange ideas. Thus was the power of printing. Book fairs then accelerated the growth in the international trade of books. Books strengthened innovation, making it possible for innovators to work together and pool ideas. It made it possible to attack the monopoly of information previously held only by the universities. And of course, what I mean by that is that prior to the printing press, very few people had access to ideas and to education. Those with previous access had a vested interest in protecting that access. The printing press democratized this information and eliminated this monopoly. The printing press also created a sort of intellectual arms race. Kings and queens needed these new weapons. They needed to be the first to discover a new land and use a new navigational system. This competition would go a long way to fuel the incessant wars of the 17th and 18th centuries, but would also transform Europe into the world's dominant continent for centuries. But if there are now facts, then Europeans needed a way to test those facts. We call that process today experimentation. The first proper experiment in European history that we know of took place on September 19th, 1648, and was performed by Florin Périère, a French scientist and actually brother-in-law to Blaise Pascal. He used a sealed tube and mercury to study changes in air pressure and density based on height. To be a proper experiment, you need 1. A carefully designed procedure, 2. Verification, i.e. onlookers, 3. Repetition, 4. Independent replication, and 5. Result dissemination. Périère was the first to combine all these factors in his altitude experiment. Now, certainly philosophers had tested theories before. Ptolemy and Galen did so centuries earlier. And the great Arab scientist Ibn al-Haytham had done some rudimentary experiments in the 11th century. The puzzle was not whether there was any experimentation prior to the scientific revolution, but why there was so little. One reason is that experimentation required manual labor, and the reality was medieval and Renaissance culture was resistant to physical work. This only starts to change in the mid to late 15th century. Second, again, the emphasis in medieval Europe was on Aristotelian logic and using logic to prove points. Before the 15th century, it was assumed there was no need to physically test something. You could prove it true or false based on argument and reason. Third, experimentation requires one to move back and forth between concrete facts on the one hand and abstract theory and hypothesis on the other. Experimentation requires a balancing act between Platonic idealism and crude empiricism. You need to be able to make the claim that general conclusions can be drawn from specific examples. Europeans simply weren't accustomed to doing this before the 15th century. Finally, as we have already covered, there was no culture of discovery in the Middle Ages. So what would be the point in experimentation? Society was entirely backward looking, and I cannot stress this enough. I know that I keep repeating it over and over again, but it's so important that prior to, let's say, the late 15th century, European society had its head turned backwards. They were always looking to the glories of the past. After the end of the 15th century, that's when the idea of progress and looking forward becomes the new European mindset. And that, my friends, is an amazing and important shift. Even Arab scientists, certainly the most advanced in the High Middle Ages, struggled to make discoveries somehow fit into their past-based cultures. The first major field for experimental inquiry in the early modern period was with the magnet and navigation. This was an easy starting point for Europeans because there was no such thing as the compass in the ancient world. So clearly, one couldn't look to Ptolemy for help. Plus, the compass and the magnet were essential in navigation, which suddenly everyone cared a lot about given the economics. By 1522, Sebastian Cabot, who sailed from England to Nova Scotia, realized that magnets do not point true north, but rather east or west of true north, depending on where you were in the globe. This was a crucial discovery because now depending on the level of variation in your compass, you could use it to determine longitude. Hence, experimentation in that case led to a novel discovery. All right, now that we've covered some of the basics of the early scientific revolution, I want to take a look at two key figures from that period, Copernicus and Galileo. Copernicus because he's arguably the father of modern astronomy, though that award might fairly go to Tycho Brahe. Galileo because he gets us into the history of the reaction to the scientific revolution, which of course there was. That brings the church and Inquisition onto the board, and I can't wait to talk about that. In the interim, if you'd like some more content, check out the links in the show notes. Got 2 down there for 2 7-day free trials. The Western Civ 2.0 and the Patreon account both offer that option now if you're looking for additional ways to support the program. The other thing that's there is the link to the website if you would just like some additional stuff. Go ahead and check it out.